I'm Kazu Ghalamkari, a postdoc at DTU. This work introduces a novel algorithm for non-negative low-rank tensor factorization based on information geometry. Information geometry is a mathematical framework that describes the geometry of probability distributions. Now we consider a non-negative normalized tensor T. If we interpret the tensor modes as random variables, the tensor itself can be regarded as a discrete probability distribution. Building on this idea, we apply information geometry to non-negative tensor factorization. Although our framework can be generalized to various rank approximations, here we focus on the CP decomposition. If the given tensor T represents discrete data samples, the reconstructed low-rank tensor P approximates the underlying true distribution of the data. Let's now see how we optimize the objective function, which is defined by the KL divergence from T to P. We consider a three-dimensional tensor space where each point represents normalized non-negative third-order tensor. The set of low-rank tensor forms a model space, and our goal is to project T onto this model space. However, this model space is not flat, making the projection a non-convex optimization problem. So instead of the original third-order tensor space, we consider a four-dimensional tensor space. In this space, we define a model space by removing the summation symbol from the definition of CP decomposition. Interestingly, this subspace is E-flat, which means the projection onto the subspace always becomes a convex optimization problem. However, our original goal is to factorize third-order tensors. To connect back to the original space, we define a data manifold D as a set of tensors that becomes a tensor T by marginalization. This manifold is M-flat, which means the projection onto the subspace by minimizing the reverse KL divergence is a convex optimization problem. We repeat these projections and approximately find the low-rank tensor P. This procedure is known as EM algorithm in information geometry, which is a generalization of the expectation maximization algorithm, and we can guarantee that the objective function decreases monotonically. We also provide a closed form update rule in each projection for various low-rank structures such as CP, Tucker, and train decomposition. We note that each step is convex optimization, but the convergence point still depends on the initial value Q1. Finally, we also provide numerical results comparing the proposed method and the existing method. Thank you for your attention.